Hey everybody, today we're going to talk about 7.4 double angle and half angle identities. We're actually going to focus on the double angles today, and we'll talk about the half angles next time. So let's kind of introduce double angle identities. So when A equals B in the identities for the sum of two angles, you get what are called double angles. So if you remember, we did like cosine of A plus B, sine of A plus B, tangent of A plus B. Well, it's saying, what if those were the same? What if A and B were actually equal? Then you would actually have what are called double angles. So let's start with cosine, just like we started with cosine in the sum and difference identities. So if we say that the cosine of 2A can really be thought of as the cosine of A plus A, because we're saying that A and B are equal, we can plug that in to the sum identity for cosine, and we can say that the cosine of A times the cosine of A again minus the sine of A times the sine of A would result in what is called our first double angle identity, because we'd have cosine squared A minus sine squared A. So there is your very first double angle identity for cosine. So if we take that cosine double angle identity and we remember a couple of key facts. So first one is we are going to remember, helps if I spell remember correctly, remember, there it goes, remember that our Pythagorean identities can be manipulated. So, for example, that cosine squared is really equal to 1 minus sine squared. We'll probably call it A. We could swap that in or replace it or substitute it into our double angle identity. So we could say, for example, that cosine of 2A is equal to, and if I replace it, 1 minus sine squared A minus sine squared A, we actually end up with an alternative version of the cosine double angle identity. So we get 1 minus 2 sine squared A. So there is an alternative version of the cosine double angle identity. And guess what? Unfortunately, there is a third version. And the reason there's a third version is because we also have that sine squared A is equal to 1 minus cosine squared A. So we could replace sine squared as well. So we'd have cosine of 2A is equal to cosine squared A minus the quantity of 1 minus cosine squared A, if I can squeeze it in there. So the double angle cosine of 2A is equal to, well, if I distribute that, I end up with 2 cosine squared A minus 1. So there is a third version of the double angle identity for cosine. So believe it or not, 3 different versions of the double angle identity for cosine. Now, the good news is that's not the case for sine and tangent. So we'll quick derive sine and tangent, and there's only one version, so it really shouldn't be that bad. So we can find the double angle identity for sine basically doing the same thing. So if we take our sum identity and we say, well, those two angles are equal, we'd end up with sine of 2A is equal to the sine of A plus A. And so I'd end up with sine A cosine A plus cosine A sine A. And you look at that and go, well, that's kind of weird, but hopefully you also realize that those are the same terms. Like, they're in the wrong order, but sine A cosine A and cosine A sine A are the same terms. So you actually have 2 of them. It's 2 sine A cosine A. So there is the double angle identity for sine. And let's do the same for tangent. You'll notice we can do the same thing. We say tangent of 2A is really equal to tangent of A plus A, because we're just setting the 2 angles equivalent to each other. And we can generate tangent of A plus tangent of A all over 1 minus the product of tangent A, tangent A. So if we simplify that, we end up with 2, let's rewrite it, tangent of 2A, so the double angle, is 2 tangent A all over 1 minus tangent squared A. So there is your double angle identity for tangent. So you need to memorize these. I know it's more to the list, but you got to memorize them. They're super important. I've got them all organized in a box here for you. So you'll notice the 3 versions of cosine and then the versions of sine and tangent. All right, so let's practice using them now that we have them. So first thing we want to look at is the directions here. It says finding function values of 2 theta given information about theta. So you're starting with theta and you're trying to find 2 theta. So that's important to recognize that that's what's going on. So it says given cosine of theta is 3/5 and sine theta is less than 0, find the double angle for each of these. All right, so let's start with sine because I like going in order. So we're going to say sine of 2 theta is equal to 2 sine theta cosine theta. All right, so we're already given cosine theta. That's the easy part. The harder part is I don't know what sine theta is, but we should be able to figure it out pretty quickly because remember, if I was given that cosine of theta is 3/5, we know the formula here. 3/5 means that this is x over r. And I'm hoping that you recognize, well, if that's x over r, that means that y has to be 4 because it's a 3/4/5. So that means that sine of theta is equal to 4/5, but it says that sine of theta has got to be less than 0, so it's got to be negative. So you could sit there and do Pythagorean theorem, but I'm hoping you recognize that it's a triple. Well, if that's the case, we have 2 times -4/5 times 3/5. So we should be able to multiply that out, and we're going to end up with, survey says, -24/25. So there is your first double angle. All right, now we want to find cosine of 2 theta. Now, remember, there are 3 different versions. They either involve both sine and cosine or just sine and just cosine. Any of them will work because if you notice, we were given cosine, we already calculated sine, so any of them will work. But what I'm going to do is I'm going to use the one that involves just cosine because we were just given cosine. So I want to make sure that I get the right value. So I'm going to go with the one that's given. So cosine of 2 theta, if we're just using cosine, is 2 cosine squared A minus 1. So again, you could use the one that has sine in it, but because I calculated that, I don't always want to depend on myself in case I mess it up. It's okay. So 2 times, this is 3/5 squared minus 1. So that's 2 times 9/25 minus 1. And so I get 18/25 minus 1, which should generate -7/25. So there is the second double angle. All right, so now that leaves us with tangent. And I'm running out of room, but I think we'll make it fit. So tangent of 2 theta. So this one's a little trickier because tangent of 2 theta, if you use your double angle, is going to be 2 tangent of A over 1 minus tangent squared of A. So this one is a little trickier because I actually have to depend on my previous answers. So we got to figure out what tangent of A is. Well, if you think about this, we calculated stuff up here with sine and cosine, so we should actually be able to figure out tangent pretty quickly because tangent of theta is really just y over x, and you know that y is -4 and you know x is 3, so we can get, it's y, negative is 3, so we should be able to get it pretty quickly, okay? So we come back down, we say, okay, well, if tangent is -4/3, this is 2 times -4/3 over 1 minus -4/3 squared. Running out of room, so I'm going to bring this up here. So 2 times -4/3 is really -8/3. This is 1 minus 16/9, which gives me -8/3 over -7/9. And I'm not going to go through the whole multiplication. I'm going to trust that you can flip it and reverse it. So 24/7. So there's your tangent double angle. Now, I'm going to put a big old or here because that is a valid method, but I think there's an easier way. And it's one of the things we've kind of talked about as we've gone through these. You got to remember that tangent is really a quotient identity. So if I'm looking for tangent of 2 theta, I could realistically just say it's the sine of 2 theta over the cosine of 2 theta, which is what we calculated already. Like, if you go back over here, we found the sine to begin with was negative 24 over 25. So negative 24 over 25. And we calculated cosine of 2 theta to be negative 7 over 25. And so, again, you multiply that by the reciprocal, you get 24 over 7. Same thing. I kind of like doing it that green method a little bit more because I think it's a little bit easier. I don't have to calculate what tangent is. I don't have to plug it in. There's a little less fractions involved. So I kind of like the green method more, but it's really up to you. All right, so let's look at example 2. Example 2 is actually doing the opposite. It's saying find function values of theta given information about 2 theta. So this time, they're telling you the double angle info. You're trying to figure out the single angle info. Okay? So it says find the values of the 6 trig functions of theta given cosine 2 theta is 4/5 and theta is in quadrant 2. 90 to 180 is in quadrant 2. So we got to find all 6 trig functions of theta given cosine of 2 theta. So honestly, I like starting with sine. So I would start with the double angle identity for cosine of 2 theta is equal to 1 minus 2 sine squared theta. And the reason I start here is because I don't know what cosine of theta is, so I kind of want to avoid that one. And the one that has cosine squared minus sine squared, and we'll show you that in a minute. So I want to go with the one that's going to give me sine. And again, it's because I'm kind of hyper organized. I like to start with the first one, so that's why I'm going to go with this one. So I go with 4/5 is equal to 1 minus 2 sine squared theta. I'm literally just plugging in from what I was given. Cosine of 2 theta is 4/5. So I subtract 1, I get negative 1/5 is equal to negative 2 sine squared theta. Divide by negative 2, I get 1/10 is equal to sine squared theta. So sine theta is really equal to plus or minus 1 over root 10. So you're going to have to rationalize. So sine of theta is really plus or minus root 10 over 10. But we're in quadrant 2, remember? 90 to 180. So sine of theta is really positive root 10 over 10. Okay? So you found the first one. That's what you had to do. But now I got to find the 5 others. So you could sit there and use the other double angle identities, but why? If I know that I'm in quadrant 2, I know that I've got a terminal side in quadrant 2, I know that it's a sine value, so this is root 10, and that doesn't look very good, does it? This is root 10, and this is 10, so I'm really just missing the x value. Just do the Pythagorean theorem, and then you can find the x value, and you can generate all the 6 trig values. So x squared plus the square root of 10 squared is equal to 10 squared. So I get x squared plus 10 equals 100. So x squared is equal to 90. X is equal to plus or minus 3 root 10. Remember, we're in quadrant 3, so it's negative 3 root 10. So now you have x, y, and r. You should be able to fly through all of these, right? So I'm going to put it on my diagram so that we can see where it is, negative 3 root 10. And this is my theta. We already did sine, so we're going to go, okay, cosine of theta. That's x, negative 3 root 10 over r, which is 10. Boom. There's number 2. Then we're going to go tangent. All right, tangent of theta is negative 3 root 10 over 10, root 10, y over x. Those cancel out. I'm left with, I did it backwards, didn't I? Good thing I caught it. Good thing I caught it. It's y over x, so that's root 10 over negative 3 root 10. So those cancel out, and I get negative 1/3. Now I'm down to cosecant. Well, cosecant's just the reciprocal of sine, so 10 over root 10, which just simplifies to root 10. And now I'm doing the secant. The secant is the reciprocal of the cosine. So that would be 10 over negative 3 root 10, which simplifies to negative root 10 over 3. And then we have the cotangent, which is just the reciprocal of tangent, which is negative 3 over 1 or negative 3. Okay, so to me, that's the easiest method. By far the easiest method. Now, the alternative is you could use some more double angles. Like once we figure out the sine of theta is root 10 over 10, instead of doing this whole process of x, y, and r, what you could do is kind of a hybrid of that and use the other double angle formulas or the other versions to calculate them. So I'll quick run through it. You don't have to do it this way, but like once I figure that out, I could use the cosine double angle identity again and say, okay, well, cosine squared theta minus sine squared theta, and I could plug into here, and that will end up solving for cosine. So you'll get like 4/5, that's the value we were given, is equal to cosine squared theta minus, well, we just calculated this, root 10 over 10 squared. So 4/5 is equal to cosine squared theta minus 10 over 100. So if you subtract, I'd actually simplify it a little bit first. So 4/5 equals cosine squared theta minus 1/10. Now you'll add it over there. So you'll get like cosine squared theta is equal to 9/10. Cosine of theta is equal to plus or minus 3 over root 10. Again, we're in quadrant 2, so you know it's negative, and we got to rationalize it, so negative 3 root 10 over 10. So you'll notice I can get the cosine using the double angle, but it's a lot longer. And then you could do the same for like tangent, and but don't. Like once you find that first value, I would just use Pythagorean theorem in our formulas, okay? But you could go through this and keep finding and using double angles. Your book wants you to keep doing it that way only because you're going to generate or you're going to work with those double angles more, and it's going to help memorize them, okay? Remember, our repetition promotes growth. All right, so now let's see about just using them. So let's simplify using the double angle formula. So it says simplifying expressions using double angle identities simplify each one. So first of all, cosine squared 7x minus sine squared 7x, which one does it look like? Well, looking at this one, I think it's a cosine double angle because the cosine, let's not blue. What am I doing? We are BA. So let's say cosine of 2a is equal to cosine squared a minus sine. It definitely looks like this, right? It definitely does. And we're basically saying let a equal 7x. Okay, so if we're letting a equal 7x, that means that this thing that we were given is really equal to the cosine of 2 times 7x. So if I had to simplify this, it simplifies to cosine of 14x. That's it. That double angle, we were given the right-hand side, and we're trying to simplify the left-hand side. So it's cosine of 14x. All right, so let's look at B. Sine of 15 times the cosine of 15. Okay, which double angle does this look like? Well, it looks like the double angle for sine. Sine of 2a is equal to 2 sine of a cosine of a. And you're going to say, Mr. Dryden, no, it doesn't. No, it doesn't. You're right. It doesn't look exactly like it, but it's pretty darn close. It's missing the 2, right? That's what it's missing. So the question becomes, well, how do I make it that? Because it's not exactly the same. You're right. So I need to make it exactly the same. Well, to make it the exactly the same, I exert my dominance, right? I need a 2. So I put a 2 in and I say, okay, 2 sine 15 cosine 15. We all agree, okay, now it's the same. But can I just put in a 2 where I want to? And the answer is no, you can't. You can't just randomly put in a 2. But what can I multiply by? And this becomes interesting because I multiplied by 2, which I can't, but I can multiply by 1, right? I can multiply by 1. So what if that 2, instead of being a 2, I multiply by 2 and I multiply by a half? So now if you think about that, that 1/2 times 2 is really just a multiplication of 1. So what we're really saying here is I have 1/2 times this double angle, don't I? 1/2 of sine of 2a. So now if I think about that in terms of 2 sine 15 cosine 15, what I really have is 1/2 of sine of 2 times 15, which is 1/2 of the sine of 30. And we know the sine of 30, I'm hoping. You get 1/2 times 1/2, which is 1/4. Now, if it doesn't look exactly like what I want it to, I have to kind of tweak it or manipulate it a little bit in order to equal what I want it to equal. So that's why I get creative and I do this fancy form of 1, which is 1/2 times 2. Okay. One more problem, we'll call it a day. So deriving multiple angles. So no longer a double angle, but 3x. So it's a triple angle. So it says write sine 3x in terms of sine x. So we want to take this and use only sine x's to write it. So I'm going to start by rewriting 3x as the sum. So I'm going to say, okay, that's the sine of 2x plus x. And the reason I do that is now I have a double angle and a single angle, and I have a sum identity. So I can use my sum identity for sine to kind of break this up. So sine of the first angle times the cosine of the second angle plus the cosine of the first angle times the sine of the second angle, which is super convenient because sine of 2x is a double angle, so I can substitute in 2 sine x cosine x. I still have that cosine x there, plus this is another double angle. I'm going to go with cosine squared x minus sine squared x times sine x. And now I'm simply going to multiply. So if I multiply 2 sine x cosine x times cosine x, I get 2 sine x times cosine squared x. Plus, if I distribute this, I get cosine squared x sine x minus sine cubed x. And you'll actually notice this first term and second term are actually like terms. I can actually add them together. So I'm going to say that's 3 sine x cosine squared x minus sine cubed x. Now, I'm getting close because I have this sine x. The problem is that cosine squared. So I got to deal with the cosine squared somehow. And I need to put cosine squared in terms of sines. Well, that's where the Pythagorean identities come into play. So this is really 3 sine x, and I can swap out cosine squared for 1 minus sine squared x minus sine cubed x. So I distribute again. So I have 3 sine x minus 3 sine cubed x minus sine cubed x. And now we got two like terms at the end, 3 sine x minus 4 sine cubed x. So there is your simplified triple angle in terms of just sine x. All right, so that kind of takes care of double angles. We'll talk about half angles next time. All right, have a good one.